The quadratic formula is going to be used to solve this equation, and where the quadratic formula comes from is we assume that the equation is in the form ax squared plus bx plus c equals 0, and so we start by identifying what values a, b, and c must take. In this case, a is the coefficient of the first term, b is the coefficient of the middle term, and c is the constant term, or the term with no variable in it. Now, the first time plugging into the quadratic formula, I recommend not trying to do any simplifying as you plug in, but just literally plug the variables in. To do that, I'll use this sort of quadratic formula skeleton here, in which I will just plug in the numbers. And always start by simplifying inside the parentheses, rather inside the square root. Eight squared is 64. For my 4ac term, I have 16 times 13, for which maybe I'll bring up my calculator to get 208. (64 minus 208) gives us negative 144 inside the radical. Now 144 is a perfect square, but because it's negative, we know that we're going to get imaginary solutions. The next thing I would do is focus on simplifying that radical. So generally, I think it's appropriate to take this piece out. Square root of negative 144. One way we can think of this is to pull out the negative 1 and write this as square root of 144 times square root of negative 1, which gives us 12 as the square root of 144 and I as the square root of negative 1. So that when I plug that back in, I have negative 8 plus or minus 12i, all divided by 8. Since our solutions are imaginary, we're going to want to write these as complex numbers. So the easiest way to simplify this is going to be to separate this out as two separate ratios all over the denominator of 8, or each over the denominator of 8. So that first term of 8 gets divided by 8, and my second term, 12i, also gets divided by 8. If I separate this out into two terms, it makes it easier for me to reduce, because now each of these is just like a fraction, common factor of 8 in this first one, leaving me with negative 1 as the whole term, common factor of 4 in the second one, leaving me with 3 over 2i. So the way I could write my final answer here would be 1 plus or minus 3 halves times I. So we have two solutions that are imaginary in this particular example. Technically, these are complex solutions with non-zero imaginary part, but it's a little bit simpler to just say two imaginary solutions. This next equation is rational, but it turns out to be quadratic after clearing the denominators. Remember that when clearing denominators, we want to multiply both sides of the equation by the LCD, and since this equation has only one denominator in it, that denominator is the LCD of the equation, and therefore I am going to multiply both sides by x, And on this right-hand side, I have to distribute that x into both terms, so I'm going to be very careful about what I have left at each stage here. On the left-hand side, it's fairly simple. X times x would get me x squared. On the right-hand side, the first product gets me 4 times x, and the second product gives me 1 over x times x. I can see that the x's would cancel out here, leaving me just 1 remaining for that term. Now, in order to solve a quadratic equation using the quadratic formula, we want to get this in the form ax squared plus bx plus c equals 0, which means that we need to move all terms onto the same side. And I always choose to move terms to whichever side is going to give me a positive leading coefficient. Since my x squared is already positive, I'm going to move the other terms and change their sign as I move them across the equal sign. That's how I account for the fact that they really got subtracted across. So that we have x squared minus 4x minus 1 equals 0. And to use the quadratic formula, I now want to identify a, b, and c. A is equal to 1, b is equal to negative 4, and c is equal to negative 1. I'll start by setting up my quadratic formula skeleton here and start plugging values in. B, negative 4, A is 1, C is negative 1, and A for the denominator is 1. Now, looking at the signs, I notice that although I have a subtraction here, I'm also going to have a negative number by the time I'm done multiplying all three of these factors together, so I can see in advance that that is actually going to turn into a plus by the time I'm ready to combine them. I can also see that minus 4 is going to become positive 4, so that first term is just 4. So we now have 4 plus or minus the square root of 16 plus 4, and this is all divided by 2 times 1, which is 2. So we have 4 plus or minus the square root of 20 divided by 2. Again, I always think it's a good idea to take the square root out of the quadratic formula and work with it separately. 20 is not a perfect square, however it does have 4 as a perfect square factor, so we can take out a factor of 2. Square root of 4 times square root of 5 becomes 2 times the square root of 5. So when I come back to this expression, I'm going to substitute 2 times the square root of 5 for my square root of 20. Here as well, I'm going to decide to simplify this by breaking it into 2 separate ratios. That's usually the easiest way to find common factors and cancel them out correctly. It's also okay to factor out a 2 from the numerator and cancel it. However, I've generally found this to be a little bit more straightforward. 4 over 2, of course, becomes 2. And in 2 times the square root of 5 over 2, the factors of 2 cancel out of this, leaving as our final answer 2 plus or minus the square root of 5. This time we have irrational solutions, so they are real numbers, but anytime that we have irrational solutions, note that it means it would not have been possible to solve this original equation by factoring. The only kind of solutions that we're able to find by factoring are rational solutions, because when we're factoring, we're essentially guessing numbers. And the kinds of numbers we guess are numbers like 3 and 4. They aren't numbers like the square root of 5, right? So we don't find these irrational solutions by the factoring method. We can now back up and see for sure that it was not possible to factor that equation.